Welcome you all to the course Database Management System. Myself, Mohammad Asifuddin Mondol, Assistant Professor, Department of Computer Science and Engineering, Narula Institute of Technology. And this is lecture number 28 of this particular course. And these are the topics which I am going to cover during my lecture. First, I will discuss about the inference rule for functional dependencies. Means in a given relation, a set of functional dependencies are already defined. From given set of functional dependency, how can we infer the new set of functional dependency? That will be covered in inference rule of our functional dependency. Then I will discuss about the Armstrong rule or Armstrong axioms. Then I will cover the closure of functional dependency, as well I will cover closure of attribute, and then I will discuss the algorithm how to determine the closure of attribute or closure of X. Means I will discuss algorithm by which we can determine the closure of attribute. So I will first discuss inference rule for functional dependency. Now on a given relation schema R, the database designer or the schema designer actually initially specifies set of functional dependency that is going to be hold or that is going to be true for a particular relation R. That means while designing a particular relational schema or a database, the schema engineer or the database engineer specifies probable set of functional dependency that is going to be true for that particular relation schema based on semantics of the data. Now, apart from specified set of functional dependency, there may be many more dependency may also exist. Those are not specified by the schema designer. So that means from a given set of functional dependency, we can infer or we can deduce or we can devise many more functional dependency. But the thing is that those deduced functional dependency must be true for any legal relation state of R. So if you look at the definition, and functional dependency X or Y is inferred from or implied by a set of functional dependency F specified on R if X or Y holds in every legal relation state R. That means X or Y, this is the functional dependency that can be inferred from or implied by, or we can say that that functional dependency can be derived. Inferred means one kind of derivation. So X or Y, this functional dependency can be derived or deduced or implied from the given set of functional dependency F if that functional dependency X or Y holds, means if that functional dependency is true in every legal relation state R. That is, whenever the legal relation state R satisfies all dependencies in F, X or Y also holds in R. And that means we can conclude that from a given set of functional dependency specified by the schema designer or the database designer, we can infer many more functional dependency that are not defined in the functional dependency set. So this is basically the inference rule. Means with the help of inference rule you can create many functional dependencies, and that concept is also known as closure of functional dependency. In the later slide I will show you the closure of functional dependency, but before that we have to know the Armstrong rule. Now what is Armstrong rule? As I have mentioned that initially the database designer specifies the set of functional dependencies F on a given relation R. Now apart from the specified functional dependency, we can infer or we can devise many other functional dependencies that are also true for the relation R. But how to deduce all those extra functional dependency from a given set of functional dependency, that is with the help of Armstrong rule. Again, I am repeating, database designer specifies the set of functional dependency F on a particular relation R initially. Now, apart from specified set of functional dependency, we may deduce or we may infer or we may derive many other functional dependency from the given set of functional dependency with the help of some rule, and that rule is known as Armstrong rules, or it also known as Armstrong axioms. Basically, there are three Armstrong rules are there, or three Armstrong inference rules are there. IR1 is the reflexive rule. If y is a subset of x and y are the attributes, and if y is a subset of x, then we can deduce x arrow y. So again I am repeating, the IR1 means Armstrong axiom inference rule 1 says that if y is a subset of x, that means, let me draw it, if y is a subset of x, then we can write x arrow y. That means actually what happened, actually the set of attribute, normally it happens the set of attribute always determine itself or subset of its attribute. For an example, suppose, let me draw it, suppose the attributes are suppose this is x, this is x, and suppose this is y. So that means y is a subset of x, then we can deduce or then we can write that way AB arrow B. So this is the first rule. Next, second rule, IR2 inference rule 2, which is known as augmentation rule. If x, y and z are the set of attributes, and if x arrow y holds on a relation R, then we can write xz arrow yz. So x, y, z are the three set of attributes on relation R, and already x arrow y, that functional dependency is already defined or holds. Then from here, or then from this functional dependency, we can write xz arrow yz with the help of augmentation rule, means just appending z over here and z over here. So this is augmentation rule. Next, transitive rule, IR3, which is known as transitive rule. If x arrow y holds and y arrow z holds, then we can write x arrow z. For example, let me clear first. X arrow y holds and y arrow z holds, then x arrow z holds. So suppose A, B, C are the three attributes, or the three, and suppose A arrow B, this functional dependency is already defined, and B arrow C, this functional dependency is already defined. That means these two functional dependency is already defined by the database designer. Now with the help of this transitive rule, we can write A arrow C. as A determines B and B determines C, we can say that A determines C also. So we can write A arrow C. So this is transitive rule. Now IR1, IR2 and IR3, these three rules actually collectively known as Armstrong axiom or Armstrong rule or Armstrong inference rule. And these three rules form a sound and complete set of inference rule. Now the meaning of sound means from a given set of functional dependency if we apply these three rule and after applying these three rule, whatever the extra functional dependency that we are deriving, all will be true and all will be hold for any relation state R of a given relation R. And complete means completeness, and the completeness of this rule means if we repeatedly apply these three rule to deduce the new set of functional dependency based on given set of functional dependency, then we'll come up with a complete set of functional dependency. We'll come up with a full complete set of functional dependency. No new more functional dependency cannot be generated after that. Now apart from the three inference rule, three Armstrong rule, we may have three more Armstrong rule, three more rule we have. They are decomposition rule, union rule and pseudo transitivity rule. That means apart from three Armstrong axioms or three Armstrong rule, we have three additional inference rule that are also useful. The decomposition rule, it says that if x arrow yz is already defined, then we can write x arrow y and x arrow z, x arrow y and x arrow z. So we are actually decomposing that part, right hand side part. And then union part, union rule, it is just the opposite of decomposition. Decomposition means you are breaking a single functional dependency into two sub functional dependency, and in union rule this is just opposite of decomposition rule. Actually we are combining two functional dependency to infer a single functional dependency. Look at how, if x arrow y is defined as well as if x arrow z defined, then we are going to union. So if you union the left hand side of the arrow, x union x means it is going to be x, and if you union the right hand side, then it will produce yz. So if x arrow y and x arrow z holds, then we can infer x arrow yz. So from these two functional dependency we can create this one. And the last one is the pseudo transitivity rule. If x arrow y and wyz holds, then wxz. So this is the kind of not actual transitivity, it's a kind of pseudo transitivity rule. Now the last three inference rule means these three rule as well as any other inference rule that we have discussed can be deduced from IR1, IR2 and IR3. So these are the completeness property. That means if we repeatedly apply IR1, IR2 and IR3, then we will get all possible functional dependency. No need to apply this extra set of rule, but yes, we can apply also. We can apply any one of the rule. Now closure of FD, already I have discussed the concept, but again, now what is the closure of functional dependency? As I have mentioned initially, while designing a relational schema or database, the database designer initially specifies the set of functional dependency. Now apart from this set of functional dependency, the relation may have many more extra functional dependencies. Now the many more extra functional dependencies that are not specified, the database designer can be deduced or can be derived from the given set of functional dependency with the help of Armstrong rule. So this extra set of functional dependency as well as the set of functional dependency, those are already defined by the database designer, collectively known as closure of functional dependencies. And it is denoted by F plus. So the set of all functional dependency that includes F as well as the dependencies that can be inferred from F. F means, let me mark it. So F means this is the already defined set of functional dependency. So closure of functional dependency means all the functional dependency that includes in F as well as the dependency that can derived or that can be inferred from F. So closure of functional dependency denoted by F plus, it means all the set of all the functional dependencies F that are already defined by the database designer plus extra set of functional dependency that are inferred from F with the help of Armstrong rule, collectively known as closure of functional dependencies. Take an example. Suppose on a relation R, the set of functional dependency F is defined. F is equal to SSN arrow ename comma bdate comma address comma d number. That means ename comma bdate comma address comma d number all are functionally dependent on SSN. SSN is social security number. And second functional dependency, which is already defined by the database engineer, is that dname comma dmgr SSN are functionally dependent on d number. So these two functional dependency constitute the functional dependency set F. Now from the given functional dependency set F, we can infer or we can deduce extra set of functional dependency that are not specified over here. Now let's take what are the extra set can be deduced from SSN. If you consider from SSN, we can write from SSN, we can, if you consider the first one, SSN arrow d name comma dmgr SSN. Why? If you look at this one, SSN determines d number and d number determines dname dmgr SSN. So if you try to remember the Armstrong rule, that IR3 rule, which is known as transitivity rule, which is in that format. If x or y is there, then y arrow x arrow y is there. Suppose this is defined, then y arrow z is there. Then what we can write from these two, we can write x arrow z. This is transitivity rule. So if you look at that, SSN determines, for again look at that, x determines y, y determines z, so we can write x determines z. So here the same is applicable. SSN determines d number and d number determines dname dmgr SSN, so we can deduce that SSN determines dname dmgr SSN. So SSN determines dname dmgr SSN with the help of IR3, means transitivity rule. Second, SSN arrow SSN, this is with the help of IR1, means reflexivity rule, means it's a attribute or set of attribute determine itself. So you can write d number arrow d name, d number arrow d number, like that. Then d number arrow d name, you also can deduce d number arrow dmgr SSN. So many more functional dependency can be deduced, but this is just for example. I am not covering all the functional dependency that can be devised or deduced. In the next slide, I will discuss the closure of FD, and I am going to take an example with more details. Let's see. Suppose R is a relation where A, B, C, G, H, I, these are the set of attributes are already defined. Means in the relation R, the A, B, C, G, H, I, these are the set of attributes are already specified, and FD is the set of functional dependency is already defined. These are the functional dependency set are already defined initially by the database designer. The question is, what will be the F plus? F plus means closure of functional dependency, means from the given set of functional dependency, what are the extra functional dependency or what are the other functional dependency can be deduced or inferred from this set FD with the help of Armstrong rule. We are going to do that here. So the first point, let me draw it. The first dependency, if you look at A arrow B and then B arrow H, A determines B, B determines D. So with the help of transitivity concept, we can say that A arrow H. So this is the first functional dependency that can be deduced or inferred with the help of transitivity rule from a given set of functional dependency. So A arrow B, B arrow H. So we can write A arrow H. This is the first. Second, what are the other functional dependency that can be derived? Let's see. If you see CG arrow H, CG arrow H is there, as well as CG arrow I is there. So if you use or if you apply the union rule, then we can write, union rule means we are going to union both side. If you union CG and CG, we will get CG. So right here CG, then arrow, and then union the right hand side H and I. So union we will get HI. So by applying union rule and with the help of these two FD, we are getting this one CG or HI. So this is inferred from given set FD. Next, let's see what are the extra FD can be deduced. Now A arrow B, A arrow C, again you can apply the union rule. So if you apply, then we can write A arrow BC. This is also true. Now fourth rule, A arrow C is there. Now if you remember the augmentation rule, A arrow C is there. Now if you remember the augmentation rule, we can write AG arrow CG with the help of augmentation rule. Why? Because G is also the part of relation. So add append G over here, append G over here. A arrow C is there, so append G, AG, append G here, it becomes CG. So A arrow CG. So this is applicable for all other functional dependency also. I am not showing it. Now next, number 5, what can be written? If you look at AG arrow CG is I have derived. Now CG arrow I is there. So what we can write again? AG arrow CG is derived and CG arrow CG, sorry, this one CG arrow H is there. So what we can write? let me show it. Sorry, it will be G. I have corrected here. So AG arrow CG is here. So and CG arrow I is here. So again, then applying the transitivity rule, we can write AG arrow I. Again, AG arrow CG is there and CG arrow H is there. So we can also write AG arrow H. Just I am showing these 6 the functional dependency that can be derived from given set of functional dependency. Now apart from these 6, we may have many more functional dependencies, but I am not going to show it over here. So these 6 extra set of dependency along with the given set of functional dependency are known as closure of functional dependency and denoted by F plus. The next is closure of attribute. Like closure of functional dependency, we have closure of attribute which is denoted by X plus. Now closure of attribute X with respect to set of functional dependency F is set of all attributes that are functionally determined by X. That means suppose we have attribute X, Y, Z. These are the set of attributes are there, and suppose X arrow Y is defined. Now closure of attribute of X means what are the extra set of attributes that can be functionally determined by X. That means X arrow Y is there. Apart from that, it may happen that X arrow YZ may be true, or X arrow Z may be true. That means closure of attribute X means set of all the attributes that are functionally determined by X. So this is known as the closure of attribute, and there is an algorithm by which we can deduce the closure of attribute. Let's see in the next slide. So the algorithm is going to determine X plus means closure of attribute X. This is the algorithm X plus. So input to the algorithm is set of functional dependency F on relation schema R and set of attribute X. And what will be the output? Suppose initially X determines Y, and suppose we have 3-4 attributes, suppose X, Y, Z and A. Suppose these 4 attributes are there, and suppose initially based on functional dependency F, it shows that X or Y means X determines Y. Now closure of X means we have to find what are the extra attribute set. What are the attribute set? Those can be determined by X. That means apart from Y, what are the other attribute set that can be determined by X is known as closure of X. That is our objective. So initially X plus means closure of attribute of X initially, that is equal to X only, means the set itself. Then we have to repeat the step. Now what is the step? We have to track the old, means X plus is the closure of attribute that will be getting changed within the loop. So we have to track the old X also, means the previous closure which is termed as old X plus, that is equal to X plus. Now for each functional dependency Y arrow Z in F, means whatever the functional dependencies are defined in the f, like in the form of y or z, for each functional dependency we have to check that condition. So for each functional dependency y arrow z in f, do that means for every set of functional dependency that are defined in f, we have to check that condition x plus superset y. That means if x plus is a superset of y, or we can say that y is a subset of x plus, then x plus will be updated. How it will going to be updated? X plus equal to x plus union z, and we're going to repeat the process until x plus equal to old x plus, means no new extra set of attributes are not generating, then we are going to stop the algorithm. Now the algorithm initially it looks very difficult, is not clear to you, but it will be clear once we explain it with an example. So let's go to the example. So consider the example. Relation is emp underscore proj, and this is the given set of functional dependency. Now we have to find the closure of SSN. So first we have to find out the closure of attribute. Now we have to first find out closure of SSN, which is termed as SSN plus. Then we have to find out closure of p number, which is denoted by p number plus. Then we have to find out closure of SSN p number as a combined, which is denoted by SSN comma p number plus. So again I'm just recapitulating it. Initially how to start with the closure of x denoted by x plus, it will be itself x, so x plus equal to x. Then for every functional dependency y arrow z which is defined in f, we have to check if y is a subset of x plus. If y is a subset of x plus, then the closure of x will be updated. How? It is going to be x plus equal to the x plus union z, means x plus whatever the value it has, it is going to be union with the value z. Let me explain. For SSN, so this is the final result, but how we get this one, let's check. So SSN, I'm writing here in short S. So SSN plus, that is equal to, initially it will be itself, means SSN, so S plus equal to S initially is the first step. Next what we have to do, we have to check every functional dependencies in F. So first one, consider SSN arrow enum. Here this is y and this is z. So SSN arrow enum. Now check whether this condition is true or false. So SSN is a subset of S plus. Yes, S means SSN here. So SSN is a subset of SSN. Yes, it's true. That means the SSN plus will be updated. And how it will be updated? SSN plus will be updated by union with the Z. So already we have SSN. So SSN union enum. So it becomes SSN. I am writing here S in short. Instead of SSN, I am writing S, comma enum. Enum means I am writing here in short only en. So this is the second step. Now again we have to check next functional dependencies. Now this is y, this is z. Now so y, we have to check whether y is a subset of S plus or not. Now the S plus means SSN plus means SSN comma en, and here y is p number. So p number is a subset of SSN comma enum? No, p number is not a subset of SSN comma en. So no use of it. Next, check this functional dependency. Now check whether SSN comma p number, whether this one is the subset of SSN comma en. No, here p number is not there. So SSN comma p number is not a subset of SSN comma en. So again, this is not going to be of no use. So ultimately what we have got, SSN plus equal to SSN comma ename. So that means the closure of attribute SSN is equal to SSN comma ename. So what is the meaning of this? We can write, the meaning of this is the closure of SSN is equal to SSN comma ename. That means we can write SSN determines SSN comma ename. I am writing en instead of ename. So initially it was defined SSN arrow ename. Now we can derive SSN arrow SSN comma ename. So these are the set of attribute that can be derived from SSN, and this is known as closure of attribute. Now consider the second case, p number. Now p number, we have to determine the closure of p number which is denoted by p number plus. So consider this one. So instead of writing p number, I am just writing p here only. So closure of p number denoted by, instead, again I am repeating, instead of writing p number I am writing only p here. So p number plus equal to, initially is the p number itself. So p, this is the first. Second, you have to check every functional dependency. Check the first one, whether SSN is a subset of p number. No, that is not going to be used. Now consider this one, whether this is y and this is z. So whether p number is a subset of p number, yes. So then the closure of p number will be updated. What we have to, we have to union with the existing p plus with the z value. P number plus equal to p number already we have, which is p comma union z, will get p name. Instead of writing p name, I am writing in short pn, means p name, and instead of writing p location, I am writing here pl. So that means the p number plus is updated with p number comma p name comma p location. Next we have to check this one. This is y, this is z. Now check whether this one is the subset of p plus. There is SSN comma p number, but SSN is not there, so this is of no use. So ultimately what we have got, the closure of p number is equal to p number comma p name comma p location. That's it. So that is how we are going to determine the closure of attribute. And these are the references you may go through for more details about the inference rule, Armstrong axiom, the closure of a functional dependency, the closure of attributes. You may go through these two books for more details.